Assalamu alaikum dear students, we're back with another video lesson. In the previous video lessons we were talking about magnetic force on a charged particle moving into a uniform magnetic field. We've learned about the magnitude of the magnetic force, we've learned about the direction of the force also using the right-hand rule, and we also use the table as well. Today's lesson is the continuation of those lessons. Alright, now of course we're going to start with three study tips, and these three study tips are very, very important. The importance of these three study tips lies in like connecting chapter 5 with other chapters that we've studied here. So for example, now the first study tip that we have, it says a magnetic force for a charged particle to be at equilibrium, Basha. Now whenever it says for a magnetic force to be at equilibrium, I need you to remember one thing right at this point here. Now at what point exactly magnetic force will be at equilibrium here? So we can say this is the first point that we have. Whenever it says for a magnetic force to make a charge to be at equilibrium, Basha, so at this point immediately we can say for a charge, let's say for a charge to be at equilibrium, all right. Basha, whenever it says magnetic force on a charge to be at equilibrium, immediately we can say magnetic force, it is equal to what? It is equal to gravitational force. Consider we have a charged particle here. Let's just write it here. This charged particle, of course, there is a gravitational force on it, tries to bring it down, yes or no? Basha, how can you cancel the effect of gravity? How can you make this charge to be at equilibrium? We've learned that if we have two forces of equal magnitude in opposite direction, then obviously these two forces will cancel each other out, and then we can say that the object or the charge at this point will be at equilibrium. This, or if we have a magnetic force that is acting in opposite direction with equal magnitude, then this charge will be at equilibrium. But we know that gravitational force tries to tries to pull this charge downward. So how do you cancel the effect of gravity? The magnetic force right, that it has the same amount, but it has to apply a force upward. The force upward so that these two can cancel each other out, and then the charge will be balanced. And the 20 blade charge, it will stay at this position here. At this point here, we can say F magnetic, it is equal to what? It is equal to F gravitational force. So equilibrium, to balance, all right, to balance the effect of gravity, and sometimes it says to cancel the effect of gravity. Basha, you can say F magnetic in order to be balanced and equilibrium and to cancel the effect of gravity, immediately magnetic force gravitational force. Obviously we know that magnetic force QVB sine theta sine nanosin lera, and magnetic force bubbling gravitational force mg lera. Basha او charge bubbling magnetity charge او motion charge velocity او magnetic field او mass charge gravitational acceleration, which is 9.81 at this point. At this point here, whichever for example, the variable that is unknown, you can easily find that one, both the magnitude and the direction as well. او یک لو خالانی که آیتمان بس یک دو پسرش دیکش من هی باب یک لپسر کن باشا كدلay direction force دبي كوبيتن here باشا. Should the force, for example, be outside basi direction magnetity direction magnetic field كده كوديك direction basi direction and bubbling direction force دبي كوبي ليرة بابا. Lera, we know that gravitational force, it is downward when ya باشا gravitational force downward بيتن باشا دبي magnetic force كرولي بيتن upward when ya when we say upward baba, you can say immediately the line upward that would be Z positive when you as a psarak man here the direction magnetic field should it be horizontal or vertical. Basha vertical it is already taken by magnetic force when you the magnetic force or magnetic field upward ben nakri. We know that magnetic force, magnetic field and velocity, each one of those are perpendicular to one another. When you magnetic field direction velocity, let's just say this is the velocity Basha. Right, you can see that if this is Z positive and upward, y-axis and bubbling x-axis the y-axis the angle between each one of these it is 90 degrees in here, Basha, between each one of those here. But point ليرة ده أجر magnetic force upward بيتن the magnetic field عيننا upward بنكرت شكا نكرت two of these be on the same direction or both parallel to one another. كات أجر force upward be the magnetic field velocity they must be in a horizontal plane باشا ما بس man plane كليتي بابا أجر if I have or use this one here but man دكريه كشان magnetic field دك y بي دكريه ودي x بيتن بس ليرة magnetic force كده بي upward بي أقل لي بي بابا ها قلت man gravitational force لخواريا كاتا magnetic force كلو سريع كاتا أو بعمل axis كان يدي كان plane كيديكا دبيت magnetic field velocity باشا أول اللي بيدبي كاتا that is the first study tip that we have باشا قلت man أجر قوتي magnetic force for a charge to be at equilibrium وخالي كم خالي دوام ماشي هر كاتك باسي acceleration يكدو بابا whenever says what is the acceleration here that would be the second study tip here whenever it talks about acceleration or says what is the acceleration immediately we can say or if a charge is moving into a magnetic field باشا هر كاتك باسي acceleration يكدو بيان acceleration is given درابو يانيش required باشا دوا كرابو Drawian Dawakrabokati, we can say magnetic force here, it is equal to what? It is equal to translational force in here. Basha? Translational force. Magnetic force akadakata say dubara dakata QVB and then later translational force akadakata baba. Obviously sine theta too, by the way, but if it is perpendicular to one another, we don't write sine theta. Force translation دكات بابا دكات mass times acceleration. Let's go equation بكاردينين أقال لي بابا أجر magnetic field ديان force وشتانا ما نبو باسي charge كردبو and then داوي acceleration كردبو يان acceleration دابو لبساركي. You can use this equation here and then after this you can find whatever that is unknown here do بابا. بس يكشيت كبابا اللي ربزانا أقال لي بي هم زاري acceleration will be what? Will be in the direction of the net force. أقال له خالي بيتم. Acceleration will be the direction of a net force here. زارو بار بسار مان هي باشا اگر داوي acceleration يكتبو هم زاري داوي direction acceleration و direction force will be the same. قال له خالي بي بسار شتيكش مان هي we need the direction of the force but they give you the direction of the acceleration. قال لي بابا direction we can say the direction of a force right will be the same direction of what and bablin later the direction of a net force here will be the same as the direction of the acceleration because the object, the particle, it will always accelerate in the direction of a force. But that is because it is accelerating in the direction of a force or decelerating in the direction of the force too. یک پسری دیکش یک نوتی دیکش معنی بابا ها قلت من ليرة أنا گرنجی و بشیتی ليرة قلت من links magnetic force with gravitational force ليرة links magnetic force with translational force باشا خالي سام بابا whenever the object says if a charge is moving in a circle basha khali sam whenever it says the charge or if a charge moves in a circle basha charge moving basha moving in a circle that's a circle the kribla clockwise and counterclockwise basha the kriya ushanish bakarbini clockwise yanish counterclockwise basha on hardi check baba let me just write it counterclockwise. For a charge, obviously, we can say immediately at this point here, we can say magnetic force, it is providing or it is equal to the centripetal force in here. Once again, magnetic force, say QVB sine theta. If it is at right angle, we don't need the sine theta. Centripetal, the mass times tangential square over the radius. Angular speedy charge if it is moving in a circle. Whenever a charge moves in a circle, whether clockwise or counterclockwise, of course, there is a centripetal force, but who is providing the centripetal force, Baba? It's a magnetic force. Chapter like we had 7 forces that provide centripetal force. One of them was a magnetic force. So this magnetic force it is always the centripetal force that is always directed towards the center, but who's providing the centripetal force here? That'd be a magnetic force. With the for example, if it asks about, let's say, tangential speed, that one, equation mass times omega squared times the radius. So, see, look at the equation, whichever we have, we can use that one. For most of the questions that we have, we'll use this equation based on the given information. These are very, very important. Magnetic force, obviously, I might tell you later, but if a charge is moving at a certain, for example, clockwise or counterclockwise, even though later we're going to study this, Griman if a charge is moving clockwise بابا. This is clockwise motion when later they might tell you just this, for example, or a positive charge moving clockwise when they might ask you what is the direction of a magnetic field here. Later بابا حركات قوتي charge clockwise and counterclockwise you have two directions already باشا. Then only by telling you, for example, clockwise direction, you already have two directions باشا. If you remember, for example, to find the direction of a magnetic field and force of شلون ما هم زاروا table أمانة BV magnetic force when then if the question only tells you, for example, a charge is moving clockwise or counterclockwise باشا, you already have two directions. How is that? Just by knowing this كاك. Manal, if a charge is moving in a, for example, circle, there's always centripetal force. Point that you agree about. At any point you take, that is totally fine. Let's say we're taking point A, Basha. You could take point B, C, D, doesn't matter which point. There is always a centripetal force which is directed towards the center, Basha. Madam centripetal force is directed towards the center is provided by magnetic force. Plane magnetic force لو خالي إيه بابا, it is directed towards the center وليرش لو خالي directed towards the center يعني شيء يعني y negative كاتا تتواني بلين أو direction force كمان هي already باشا دي أقل point تشدي كبو أقل ليرة وقري بابا دبانو أي دروات السريع ونيا دار بي y positive but we're not going to take that ونيا أقل لو خالي وقري force كا دبيتا x negative because it is moving or pointing towards x negative ونيا دي أقل لو خالي وقري force كا دبيتا towards x positive باشا أو direction force كا. Now we know that it is moving clockwise when adi direction motion ke rekle baba. Isn't that moving clockwise? Basha. Kata agar lera khala ke wagri, isn't it pointing baba no direction motion ke? Yes or no? Basha kata o zani. Now at this point here, direction of the motion at this point baba gadlibi, it is pointing towards x positive. And now the only thing that is left is the direction of a magnetic field, and that is obviously is going to be z when it is either z positive or z negative. But this is what you can do always. Now what if, for example, you can use this one here. Let's find the direction of the magnetic field at this point here. Magnetic force it is pointing towards y negative. And by the way, you need to know this one so that you need to know what is the type of the charge. So at this point it is positive. So now we know that it is the magnetic force out of the palm. Is that magnetic force y negative? So remember, y negative. So your palm is facing this way. What about the direction of the velocity, baba? Direction of velocity x positive. This x positive. So how can I do this? If I do this, would that be correct? So my palm is y negative. Velocity is x positive. What about the magnetic field? My four fingers are pointing upward, so we can say z positive at this point. And again, for example, what if it was a clockwise, but what if it was a counterclockwise direction here? Right? This is counterclockwise direction. I still have a positive charge, but I'll take a point here. You could take any other points here. Basha, you get a point that you baba. What would be the direction of a magnetic field here? You only need two things at this point here. Direction force is always directed towards the center, baba. That would be F centripetal is provided by F magnetic. At this point, direction force is x positive. Here's x positive. What about the direction of a motion, baba? It is the direction of a motion. You can see that it is what? It is counterclockwise. Later at this point here, what the direction of velocity, which is towards what? Towards y negative. You can see that that'll be towards the bottom of the page, which is y negative. Now, can you find the direction of a magnetic field? Obviously, yes. But man, do better direction magnetic force, okay, baba? It is this time towards x positive, where positive charge is shakata. Your palm must facing x positive, direction of velocity, it is y negative. So how do you do y negative? So this is y negative, you can see that. So magnetic force, y negative, that would be velocity, and you can see that my four fingers are pointing into, which means it is z negative or into the page here. This is how you can tell the direction of magnetic bubbling, or you can, by the way, you can have the direction of a magnetic field velocity by knowing two of these. Of course, you can always find the third direction easily. Basha, point ke zozor agar lo khala nabi o lo zarish hati to baba prisna ka hitsi le barke lager clockwise و magnetic field ke bono aibu positive charge bo or the bita no agar habuna hum zare. Whenever it says clockwise or counterclockwise, you already have two directions. Just write them down and you can find the third one. That easy. Basha, استاكم. بس summarize study tip ashkeno baba. These 3 study tips are very important. Gutman Yakaman says for magnetic force for a charge to be out of equilibrium, I got lo khali bizozo gringa, basha. To be out of equilibrium, that one لخوش تندق وشي دي كش إضافة كي بقى قطمان equilibrium يعني قر say balance ونيا يعني قر بلا cancel the effect of gravity on همي يكش تباشا. That is for a charge to be out of equilibrium. غير قطمان moving charge قطمان بكاتا وندا if acceleration is given or required, right, or required. There is قطمان whenever it says the moving charge move in a circle, you can say, or you can say clockwise or counterclockwise, Basha. Clockwise or counterclockwise. Here you could use this equation right here. What's that? How can we use these study tips in questions here? The first question that we have is the following question here. What does it say? It says a proton here, Basha. The proton moves eastward in the plane of the Earth. We have a proton, Basha, that is moving in the plane of the Earth's magnetic equator, where Earth's field or magnetic field points north and has a magnitude of this much. What velocity must the proton have for the magnetic force to just cancel gravitational force? Here specifically tells you for the magnetic force, that is F magnetic, to cancel the gravitational force. And we said that whenever it tells you this, always magnetic force it is equal to magnetic force in here, it is equal to the gravitational force mg. Magnetic force, we know that is QVB. Right, and you can see that these are it has to be a right angle, right? So sine mg dakata F magnetic Fg dakata mg here, right? That is the equation you need to know. These two, if they are equal in magnitude and opposite in direction, then these two will cancel each other out. Basha. Gutman the velocity man de babalera velocity ke subject V dakata say dakata mg divided by q and this b here. So all you have to do is just do the math and you will find the answer. Now, but I got low mass AB baba. This would be the mass of a proton, which is 1.67 times 10 to the power negative 27 times gravitational acceleration, that is 9.81. Charge protonia, which is 1.6 times 10 to the power negative 19 times the strength of a magnetic field, command here, which is 5 times 10 to the power negative 5 Tesla. All you have to do is just do the math. You will find the velocity of the charged particle, which is going to be 2 times 10 to the power 2.0 times 10 to the power negative 3. That is going to be not negative 3 though, right? Is it? It is negative 3 meter per second, Basha. Negative 3 meter per second here. That is the velocity that the charged particle must move in order inside a magnetic field in order to cancel the effect of gravity, Basha. This is how you can solve the questions here. It doesn't ask about the direction here, so we don't have to worry about this point here. But if it needs the direction, then enough information must be given regarding the direction so that you could solve the question, and that is how easy it is, Basha. All right, so that is for this question here. Now we have another question which is also related to these Baba study tips, Baba. What is the next one here? I get to my shop. It says what? It says a proton. So we have a proton here first. There is a positive charge. So here's a proton, a positive charge. What is wrong with this? We have a proton or a positive charge. So raise these, I don't know. Protonic man here. What is wrong with this? Protonic man here, Baba. It moves at this much meter per second. So this is the velocity here. Basha. It says horizontally at right angle. Obviously, the angle we can say theta is 90, so you don't have to write it because sine 90 is 1. It says to a magnetic field. What is the strength of a magnetic field required? So we need the magnitude of a magnetic field to exactly balance the weight of what? The weight of the proton here. Whenever it says to balance the weight of a proton here, didn't we say F magnetic must equal to FG. And then after that, and keep it moving horizontally. So because it says what is the magnetic field strength to balance the effect of gravity, good man, هكاتك to balance the effect of gravity وشتانا دي ديك ستلن F magnetic دكاتا it is equal to F gravitational F magnetic دكاتا QVB باشا QVB right sine theta كي بينا بابا it is equal to mg. هستاك B man there B دكاتا mg divided by what? Divided by QV, and then all you have to do just plug in the numbers and you can find this one here. Bashagatman protoni shamasi protoni was 1.67 times 10 to the power negative 27 times the gravitational free fall acceleration 9.81 here, and then divided by the charge, which is 1.6 times 10 to the power negative 19, multiplied by the velocity of the particle, which is 2.50 times 10 to the power 6 meter per second. All you have to do, just do the number. Of course, now you can find the answer here, which is going to be 4.1 times 10 to the power 4.1, right? 4.1 times 10 to the power negative 14 Tesla. This is how much, or this should be the strength of a magnetic field in order to cancel the effect of the weight in here. Magnitude. So magnitude and that is the strength there. All right, the second part of this question here says what? Says, should the direction of a magnetic field be in a horizontal or a vertical plane here? Direction magnetic field, okay, should it be in the vertical or horizontal plane? Gravitational force tries to pull the charge down one, yeah? FJ. How do we balance the effect of this one here? Magnetic force the be upward beaten here. Up beaten because this force here, it is downward one, yeah? Gravitational force it is perpendicularly downward, baba. This is gravitational force that tries to pull it downward. So magnetic force they be upward beaten. But if the magnetic force is upward, the magnetic field is an upward beaten. Madam magnetic force is upward kata, the magnetic field must be in a horizontal plane. It could be either X or Y, we don't care. Basha al-Muhim, the magnetic field that is not in a vertical plane, it is in the horizontal plane. Basha the magnetic field this is magnetic field, this is the velocity on him, this is up, where you can say Z positive, the beta X, or the beta Y, it doesn't matter at this point because they're not asking for it. But you know that the angle between each one of these it is 90 at this point right here. And that is the answer to this question, Baba. With the direction of force, of course, the direction of a force must be upward in order to cancel the effect of gravity. Still related to this question, or these study tips here. What does it say, Baba? We have a proton moves at a speed of this much. So this is the velocity here. You can see that at right angle. So go 90 to a magnetic field with a magnitude of this much. So here is magnetic field. Says find the magnitude of the acceleration here. So whenever it talks about magnetic field and all that, if acceleration is given or required, what is according to the study tip that we have? The magnetic force, it is equal to what? It is equal to translational force in here. Yani magnetic force dakata QVB, the translational force dakata mass times acceleration. And how do you consider that one? Mass times acceleration. See here, what we're looking for is the acceleration. What is the acceleration equal to? Acceleration dakata QVB divided by what? Divided by the mass. But mass proton, okay, of course, because there is a proton or the mass of the particle here. Yeah, charge proton, it is 1.6 times 10 to the power negative 19, Basha, times the speed of, or the velocity of the particle, which is 2 times 10 to the power 7, right, times the magnetic field strength, which is 0.1 Tesla, Basha, divided by the mass of a proton, which is 1.67 times 10 to the power negative 27. All you have to do, just do the math and you'll find the magnitude of the acceleration. And let's see what is the magnitude here. It only says the magnitude, so no directions needed, which is going to be 1.9, as you can see here. It is 1.9 times 10 to the power 14. 1.9 times 10 to the power 14. Since that is the acceleration, it is meter per second squared, and that is the answer to this question. All right, now moving on to another question here. Basha, still related to the study tip. See the importance of the study tip, Baba. These are very, very important, so make sure you practice them. Proton moves perpendicularly. Again, so we have a proton, moves perpendicularly, the angle is 90, to a uniform magnetic field B. Basha says with a speed of this much, so we have speed here, it's 1 times 10 to the power 7. Basha, and experiences an acceleration. Experiences an acceleration. So this time the acceleration is given Basha, and obviously it is a magnetic bubbling charge inside a magnetic field. So immediately we can say F magnetic F translation Yanish QVB right away mass times acceleration. Basha, this is the equation you need to remember. The acceleration is this much, 2 times 10 to the power 13, in the positive x direction. Now I need you to underline this for yourself as well. This is the direction of the acceleration. Direction force will be what? Will be the same. Basha, this is for, we can say, later uses. Basha, when its velocity is in the positive x or positive z direction, that would be the direction of a velocity, determine the magnitude and direction of the field in here. So now at this point here, we have, or we need to find two things here, magnitude and direction of the field in here. So that is the equation that you need to begin with. So here, magnitude of the magnetic field, the mass times acceleration divided by what? Divided by Q times V here. Basha, massa command send it is a proton one, yeah. Massa 1.67 times 10 to the power negative 27 times the acceleration, which is 2 times 10 to the power 13 meter per second squared, divided by the charge, 1.6 times 10 to the power negative 19, multiplied by the velocity, which is 2 times, or 2.0 times 10 to the power, times 10 to the power what? Times 10 to the power 13. Wait a second. This is the acceleration. I need the velocity here. What is the velocity? It's 1 times 10 to the power 7. 1 times 10 to the power what? 10 to the power 7. Did we use the, okay, we used the acceleration correctly, and there's this speed, which is 1 times 10 to the power 7 meter per second. Now all they have to do is just do the math, and you can find the magnitude of a magnetic field strength in here. So let's see, what is it equal to here, Basha? All right, let's just move this one here. The magnitude is equal to 2.1 times 10 to the power 2.1 times 10 to the power negative 2. That is Tesla, was negative 2, right? Negative 2 Tesla. This is the magnitude of the magnetic field. But what is left, Baba, is the direction of the magnetic field, right? So how do you find the direction of a magnetic field? This is the magnitude of a magnetic field. And why are we using this equation? Because the acceleration is given here. Now, regarding the direction of a magnetic field, Baba, we're going to do this one here. Okay, so we'll say this one is extra, but we'll just say B, V, and magnetic force in here, right? So as you can see here, the direction of the velocity was positive Z, because that's what the question says. Now, if you notice, direction of force, but instead, direction of acceleration, and we said that the direction of the acceleration will always be in the direction of a net force in there. Direction of acceleration, x positive. In that case, of course, what is left for the magnetic field? X money, Z money, Ch my to Baba, Y is left one here. Direction of magnetic field, okay, must be in Y axis. Is it Y positive or negative? Now you'll have to use the right hand rule. Basha? Direction force is positive. The direction of the magnetic force X positive is actually here, X positive. Or you could just point it this way here. The direction of the velocity is Z positive. How do you do this? That is not Z, obviously, so you'll have to flip it. Would this be correct if I do this now? Right. Remember, I'm using the same perspective that you're doing here, or you have. So the force is X positive, as you can see here. The direction of the motion, it is Z positive, which is upward here. So what is the direction of a magnetic field? You can see that it is towards the bottom of the page, and Y positive, yeah, negative, Y negative, well done. And this is how you can get the direction right. So at this point here, you could just say Y negative towards the bottom of a page. Look at the option, or you could even say south, whichever that is given, that would be correct. So of course you could keep it in negative y, because that is what is given here. This is how you could solve these questions that are related to this. Now, moving to the next question here, so you can see y negative there. Moving to next question, or another question that is related to the study tips that we have. Basha, we have another question here. Hey, Baba, what does this question say? This is the only, or you can say the first question that we have an angle. Basha, yani the charge is not at a right angle. Basha. Once it is entering or inside a magnetic field, let's say a proton travels with a speed of this much. So again, we have a proton that is a positive charge, Basha, travels with the speed of this much. So this is the velocity here at an angle 37. Watch this, Baba. At an angle 37 west of north. Hamzari Baba. Angle it is always, we've studied this before. The angle is always with the second word. Write this as a note in here. The angle is always, the angle, Basha, is always with the second word. Is always with the second word. With the what? With the second word in here. So for example, here says west of north. Got that? The angle is with the north. That is the first thing that you need to notice here. It says a magnetic field of 0.3 Tesla points to the north. Basha, that is the direction of a magnetic field. Determine the following here. The first thing you need to find is the magnitude of the magnetic force on a proton here. Find what? The magnitude of a magnetic force on a proton. Well, that is easy. All right, magnitude of a magnetic force. So we'll just have our, like the normal magnetic force equation, and that is QVB. And then this time you'll have to write sine theta, because it is moving into a magnetic field, which is not our right angle. So let me draw this one here as well. So here is the, by the way, we have a magnetic field. This magnetic field that is pointing north. That is what the question said. Basha, the direction of a magnetic field that is pointing north. Let's just draw some directions here. These are pointing to the north in here. Now, what about the direction of a velocity here? Now, the velocity is at some angle, or you can say, Basha, Gutman, it is 37 west of north, right? 37 west of north. So let's say this is the direction of a motion here. You can analyze this now to two components here, right? This is the velocity. Okay, let's write a few things here. This is magnetic field. Okay, this is a magnetic field in here. And this is going to be the direction of this blue here. It is the direction of the velocity here. But Gutman, angle kebaba is always with the second word. Clearly, this is north, south, Gutman, east and west, Basha. So now the angle is west of north, Gutman. It is always with the second word. This is 37 here. Now, there is also, you could do something else, Baba, here. Gutman, you could analyze this component here, this velocity here. Let's change the color here. This is V. But now you could make this side here, or if you take a component here, this side becomes V, obviously, this is the angle width, so it becomes cosine 37. Cosine 37. Basha. لا أكيد كإيرة بابا دبيتا 37. ولا إيرة دبيتا V sine 37. Now you can see that this angle it is, or you can say this component, it is the perpendicular component. Basha, which component is providing the force? How component A كواب? It is, for example, on north, because this component is also pointing north, Baba. The creative velocity of magnetic field, they both pointing the same direction. يعني هل بمعنى ايش دي كبابا؟ The velocity of magnetic field will be parallel to one another. كاتا أو component هي فاكتة تشينيا. باشا. Later, this component is the one that is perpendicular to the magnetic field and produces the magnetic field. But you don't have to worry about this one now. Whatever the angle is, just use sine of that angle and that'll be it. Well, just use the component that is perpendicular, you can say, Basha. And again, that'll be the answer without any problems here. Zohar Basha. At this point here, Baba charge command send that. It is obviously 1.6 times 10 to the power times 10 to the power negative 19 times velocity command send that. The velocity is 3 times 10 to the power 6. Basha. And then magnetic field command, it is 0.3 Tesla times sine Ch5 sine 37 أقعد لو خالي بيتن here. Now you can find the magnitude of a magnetic force which equals to this much Newton, whatever it is. Let's find out how much it is. It is 8.7 times 10 to the power negative 14. 8.7 times 10 to the power negative 14, that is going to be Newton, and that is the answer to this question, or the first part here. Now, the second part says the direction of the magnetic force on a proton here. How do you find the direction of the magnetic force on a proton, Mava? You could still use the table that we were using earlier here. Direction of a magnetic force in here, B, V, and then we can say magnetic force. Now, with my later direction of velocity, yeah, first of all, let's start with the direction of a magnetic field. It is north, right? North, yani y positive. What about the direction of a velocity, Baba? Now, we said which component provides the magnetic force? Good man, component A, تكون velocity اللي رد بيته do component. Let me rewrite it, Baba. Divide it كنا. Velocity بونوعة. This velocity can become two component. يك كان بيته V cosine or V, or يديك بيته C, or يديك بيته V sine. So which one of these component would provide the magnetic force? Good man, nakri or V cosine wagri baba, because this is parallel to the magnetic field. I'll have to use V sine component here. But V sine component is that really baba. This one is pointing towards X negative one, so you can use X negative here. Basha. And then what about the magnetic force in here? So we have Y, we have X, got a magnetic force. Is that positive or negative? Let's just find out. Well, اگر خود لكجنا كزورا سيدة واني هر direction كي وقري زوزورا سيلة دردتي. Magnetic field use the forefinger first. That is Y positive. So upward, you could say up the page here. Direction motion it is negative X here. Got the direction force that would be out of the palm, which is we can see that into the page, or Z negative. هو قالوا شام بكارني بابا زوزورا سيا ما أنه magnetic field كيا باشا direction motion كيا right بونوعيا. That is the velocity here. هذا تواني زوزورا سيا لذاتي هم بنزكانت كيوا 90 وقري. هذا تواني بونوعيا وقري و 30 بابلين أو 90. This 37 one, yeah? If you just do this one here, that is the same thing. You can see that your palm is still facing into the page. It makes it easier. Basha? That is regarding this question too. Let's move on to another question. Or perhaps to the third part, I guess. No? Yes. It says the proton's acceleration as it moves inside a magnetic field. Because it talks about the proton's acceleration, Baba, once again, this magnetic force that we just found, right, we can say it is equal to mass times the acceleration here. Gutman, the translational force. When you Malera, QVB, and we just found the magnetic force in here, and then whatever the magnetic force, it is equal to now translational force, mass times acceleration. Acceleration the magnetic force, the one that we just found, and then divided by the mass of a proton, right, which is 1.67 times 10 to the power negative 27, Basha, and that'd be it. What was the force? It was 1. What? Man, force command sembu baba force ka. It is 8.7 times 10 to the power negative 14 Newton. You just do the math, you can find the acceleration. What is the acceleration equal to? It is equal to 5.2 times 10 to the power 13, that is meter per second square, since it is the acceleration here. That is how easy you could do these questions, very easily. Now, another question here that we have says what? A proton moving perpendicular to a magnetic field of strength of on the Baba. I get luminally Tesla because students, for example, ask me, Mr. What is meter Tesla? That's not meter Tesla, Baba. I got Levi. This is milli Tesla, which is 10 to the power negative 3. I mean, I should have not said that, but okay, yalla there. Just knowing that there are some of you actually calling this one meter Tesla, so don't do that, right? Experiences a magnetic force due to the field, which is this much is the force. Calculate the following: the speed of the proton. The speed of the proton. Watch this, Baba. Moving perpendicular to a magnetic field, Basha, strength of this much, experiences a force of on that, calculate the following: speed of a proton. Now, of course, we know that magnetic force, the kata Q, VB sine theta. And yeah, this one says right angle, we don't have to say sine theta at this point here. Data, it says calculate the speed of the proton here. Speed the kata magnetic force, let's say QV, one, yeah, or QB, my bad. QB. Zorbash. Magnetic force command the Katsan Baba. Magnetic force it is given. It is 4.5 times 10 to the power negative 21 Newton divided by the charge of the proton, which is 1.6 times 10 to the power negative 19, multiplied by the magnetic field, which is 3.5, not Tesla, huh? Negative 3, that is Tesla. So you do the math, you'll find the speed of the particle here. So what is the speed at this point here? Speed كده كانت 10, speed كده كانت 8 meter per second. 8 meter per second. That is the speed of the particle. No direction needed. By the way, whenever it says the speed of the particle, that is already the magnitude of the velocity. Basha, I get direction. Okay, perhaps it would have said what is the velocity, both magnitude and direction. But little madam just the speed, so we don't have to do that one there. All right, now the next part, which is new, it says the kinetic energy of the proton here. Basha, how do you find the kinetic energy of the particle at this point? For the kinetic energy, we can say, what is kinetic energy equal to? We'll say kinetic energy, based previously we've learned it is equal to 1/2 mass times what? Mass times velocity squared in here. So, or speed squared, Babylon. 1/2 times Basha, it is equal to, all right, so it is equal to 1/2 times the mass, Basha. Mass كمان سندا, it is 1.67 times 10 to the power negative 27 times the speed squared, and we just found the speed in the previous part in here, which was 8, but don't forget the squared, so you just do the math, you'll find the kinetic energy, which is going to equal to this much in joules. Allah, let's see how many joules it is, Basha. So the answer is going to be 5.3, right? 5.3 times 10 to the power negative 26 joules, and that's the answer for this question. See, very simple, very easily. Of course, we have similar questions like this one in Wizari, so be careful. Of course, these questions will be in Wizari. Like, for example, this one here. Basha says, moving, Basha, in a magnetic field of this much experiences a force of onda, but not speed Baba. So you have to find the speed yourself, and then after that, you can find the kinetic energy. So give it a try and then solve this question for yourself, Basha. All right, now moving on, charged particle and bubble in a charge moving through a magnetic field follows a circular path. What exactly is this now? Now, so far we've learned about this. We said if a charge goes into a magnetic field, there will be a magnetic force on it, but this magnetic force, it is maximum if a charge moves into a magnetic field at a right angle. It is going to be 0 if it is going to the magnetic field parallel, and it is sort of like between, let's say, 0 and maximum if it is at any other angles where the angle is between, the angles between 0 to 90. So what exactly are those things here? We have 3 different situations we can say, Basha. So we have a magnetic field. So Babylon KCACM. So, all right, so if a charge moves into a magnetic field, let's say this is the direction of, all right, let's say here's the direction of, as a matter of fact, no, let's just do something else. If, let's say here's the direction of a magnetic field, a uniform magnetic field, Basha. So what exactly happens if a charge moves into a magnetic field at a right angle? You can see that. So let's say here's a charge, a positive charge or negative charge, doesn't matter. What happens if it moves into a magnetic field? We've mentioned that it will end up moving, so let's just write it here, right? It will end up moving in a circle, right? So here's what exactly happens here. So if a charge moves into a magnetic field at a right angle, assuming that the magnetic field is applied uniformly, so the charge cannot exit easily because the charge is applied. So in this case, the charge will move in a circular motion here. Whenever it moves in a circular motion, magnetic force F centripetal, once again QVB, sine theta, because it is 90 degrees, so we don't write it. The mass times tangential speed squared. The radius it is also equal to mass times omega squared times radius. It's specific mania that we could use mass times omega times radius, but of course, what if, for example, there's another question that is made that requires this equation? That is totally fine. That is what happens if a charge moves into magnetic field at right angle, Baba. So it will end up moving in a circle. Circular motion, positive, negative, doesn't matter, Basha. That is one thing here. And how do I know it will move in a circle, Baba Tamasha? Man, at this point here, you can see that the magnetic field into the pitch, this direction of motion is positive, right? So at this point, there will be a magnetic force on the charged particle here that makes it move, for example, upward when you. So now if it is moving upward already, you can see that. Now this is how it is going to move now after there will be a force on it upward. At this point here, you can see that. So there is the force. You can see that this direction of a force. At this point here, this direction of a force, which makes it move into this direction. At this point here, if you do the right hand rule, you can see that the direction of a magnetic force is downward. So at this point, the direction of a magnetic force, you can see that it is what? It is towards the center here. This is the reason why the charge will end up moving in a circular path. So you can say the centripetal force is provided by magnetic force. That is the first point we can say, Basha. Now, and by the way, there's one thing you need to know, Basha. This magnetic force, Babi, and this centripetal force, we can say that it is perpendicular to both V and B, Basha. This magnetic force, you can see that. It is, if we take, for example, a point here, direction of motion indicator is Y positive. This is obviously Z negative because it is into. You can see the angle between these are 90, and also this magnetic force, it is at a right angle to both Y and Z here, or you can say the magnetic force, it is at a right angle to both what? To both V and B here. Basha? And this is the reason why it doesn't affect the magnitude of the velocity. And magnetic force and centripetal force, it does not make the charge, the centripetal force, it does not make the charge speed up or slow down. It can only change the direction of the charged particle here. Basha? It does not affect the magnitude of the velocity. What if the charge moves into a magnetic field but parallel to a magnetic field? Previously, we've learned about this one on here. And if this is the magnetic field direction, assuming that this direction of a magnetic field, what happens if a charge moves into a magnetic field at a right angle? Parallel to that. As it could be the same direction or opposite direction, doesn't matter. Be same direction or opposite direction, as long as it is parallel. Got our magnetic field there, and this is in the direction of the motion here. Basha? And then this could be the direction of motion. These are all magnetic field. At this point here, you can see that magnetic force, we've learned that magnetic force the QVB sine theta. Now this sine or this theta is between V and B, right? That is the angle between the two. So what is the angle between the two? This angle is 0 if it is same direction. It is 180 if it is opposite direction. At both cases, sine 0 and 180 Baba is equal to 0. The magnetic force so we can say that the charge will continue moving through the magnetic field unaffected. يعني بناء magnetic field كده درا بابي وهيت affected يعني affected شيء لسه هبيتم. عشان يعني it will just continue. What if a charge moves into a magnetic field, for example, but this time at some angle? يعني let's say the angle it is bigger than 0, but it is less than 90. So once again, let's say this is the direction of a magnetic field. This direction of a magnetic field, and then you will notice that here the charges. By the way, all these magnetic fields are uniform magnetic field. If they are spaced out or if they look non-uniform, that is just me drawing. Otherwise, these are all uniform magnetic field in here. Now, the next thing that we have is if a charge is moving into magnetic field, good man, at some angle here, just like, for example, like this one here. Let's change this color first. And this would be the angle which the object is moving into a magnetic field. Now, let's move this one a little bit here. So, Baba, take a look. Listen to this, because this is something very important. Now, this is V, and this would be the direction of a magnetic field here. As you can see here, there is some angle where this charged particle moves into a magnetic field. What exactly happens at this point, Baba? Is that, whenever you have angles, you can always turn that into a component here. But let's change the color back, making sure it's this. There be two component. One of the component that is going to be parallel to the magnetic field, and the other component is going to be what? It's going to be perpendicular. Now, this component here, let's just give the same color for now. This side here becomes V, because this component is with the angle, so it becomes V cosine theta. V sine theta. Whatever the angle is. V cosine theta, you can see that these two are parallel to the magnetic field. And because it is parallel, this charge will, or this component is not affected by the for example, by magnetic force. Why? Because these two are parallel. So we have a component where it allows the charge to move in a straight line here. That is for this component. It allows the charge to move in a straight line here, right? That is for this component. What about for the perpendicular component? We know that if a magnetic field, if the velocity is perpendicular to the magnetic field, we've mentioned in the first case that it will move in a circle, correct? As a combination of these two, Baba, right? These two magnetic, these two components for this charge, this is the charge now. So assuming that this is the charge, it will both move horizontally and it will move perpendicular in a circle as well because of this component that is parallel. What will it do here? Because of this perpendicular component, the charge will move in a circle here. But because of this horizontal component, it's almost like it is moving in a circle and somebody's pulling the charge or pushing the charge forward. So as a result of this, this is how it is going to end up moving, Basha. And now this is the path that this charge would be following here. Basha, it's like a springy path, you could say. Basha, what do we call this path, Baba? We call this path helical path. Helical path. Oh, it's got the helical path, Baba. But man, charge moves into into the magnetic field at some angle. Baba, but man, angle would be parallel, keeps moving unaffected. Angle would be perpendicular, which makes it move in a circle. As a result of these two combined, the charge will end up moving, for example, both in a circle and horizontally as well. As a result of this two, there will be a path that is called helical path. So this is what happens at each one of these cases. These are the three cases that we have. If it is moving into magnetic field at a right angle, it will move in a circle. Parallel B, it will move unaffected. There's no magnetic force. If it is at some angle that is bigger than 0 but less than 90 path helical path. Force maximum, force minimum, force it becomes something in between. You can see that if the angle is 90, obviously it would be half of maximum. Sine 90 sine 30 half. These are regarding this one here, but don't forget, Baba, man had to move in a circle, clockwise or counterclockwise, immediately magnetic force the kata F center parallel, which we've explained earlier. These are what we have, and Gutman later, Baba, what happens when a charged particle moves into magnetic field at an angle. Gutman later, the velocity of the particle can be split into two components. Component parallel, that would be unaffected, but the other component that is perpendicular, right, it will cause the particle to follow what? To move in a circle, obviously, causing the particle to move in a helical path along the direction of a magnetic field. If a charged particle moves into a magnetic field at a right angle, moves in a circular path, I get a parallel, it will move in a circular line. If it is at some angle, it will be helical path. Later بسارك man here. طلع singly charged positive ion بابا. أقول لو خالي بيشتري بس اشتك ما كتبوا. قال لي بيدبو بيكتمان for the magnetic force will write QVB. Why? باشا. أديك charge if it is not a single charge, for example, then whatever the number of charge, you could just multiply by that number. When you later, instead of for example, a particle here, we have an ion here. Like instead of saying a proton or a neutron, or whatever the charge is. Got out of the hand. Let's do this one again. Oops. Okay. Seriously? All right, so that is the point where you have to do this. All right, so what exactly do we have? Okay, so a singly charged positive ion. So you can write this a charge, we can say, it says a singly, you can say a charged positive particle one, yeah, and a positive ion, you could say. So when it says this, Baba, just be careful of that here. It says when a positive or a charged positive that is only one charge, Basha, has a mass of this much, so this is the mass, okay, moves clockwise. I need you to underline this for yourself here. Clockwise with the speed of this much. Right? Whenever it says clockwise, that means there is a magnetic force. Obviously, it says moves this much clockwise with the speed of this much. Right? It says the positively charged ion moves in a circular path. That is also another keyword in here. It says circular path. Basha has a radius of this much, but there's a centimeter. Careful here. You have to convert this. Find the direction and the strength. So direction and the strength of a uniform magnetic field through which the charge is moving here. Madam says circular motion or clockwise and all that, Baba. And we have magnetic field, Kati. Immediately we can say magnetic force, let's try. In this case, of course, we can say immediately magnetic force, the centripetal force, Baba. Magnetic force, QVB, Basha. Sign in this case, of course, it is equal to the centripetal here. Centripetal mass times tangential speed divided by the radius. How do I know I'll use this? Because it gives me speed and also gives me the speed here. So this is the equation that I need to use. So the question says find the magnitude of a magnetic field, Baba. All right, so let's just keep this one here for a second. So magnetic field, that's it, just use cross multiplication. That is going to be mass times tangential squared and then divided by, we can say Q V times what? Times the radius. That is all they have to do. Now, one velocity, you could say, cancels out with this one. So what will be left now? We can say at this point it becomes mass times velocity, and then divided by what? Divided by Q times the radius here. Q times the radius. Now, just all they have to do next, just plug in the numbers now. What is the mass of the ion here? It is 6.68 times 10 to the power negative 27. Basha, and then multiplied by the speed of the particle. What is the speed of the particle? It is 1 times 10 to the power 4, Basha, that is 4 meter per second, and then divided by the charge of the positive ion. What is the charge for the positive ion? It says a single positive one, yeah? So if that is the case, we'll just use 1.6 times 10 to the power negative 19. Bash. What else do we have? It says the times the radius one, yeah, by this Baba. If you convert that to meter, that is going to be 0.03 meter. That is everything you need to do now. Now, the next thing is just, do the math and you'll find the magnitude of a magnetic field for this one here. So let's find out what is equal to, what is the magnitude of this much. It is 1.39 times 10 to the power negative 2. 1.39 times 10 to the power negative 2 Tesla. And that is the strength of a magnetic field. And that's it. The next part says what? It says both magnitude and direction, right? So this is the magnitude of a magnetic field strength here. And the direction, now remember, whenever it gives you clockwise or counterclockwise, you have two things already. When you did the clockwise, it's a positive and negative. Positive one, we have a positive charge, and it says clockwise. So this is clockwise. But you can now, whenever it says clockwise or counter, you can take a point at any point here. It is totally your choice here. Let's take this point right away here, right? If that is the point here, good man, there is always centripetal force in here because there is provided by magnetic force here. Because it is moving clockwise, clockwise direction, it is in this case, when you always for the direction, just use a tangent here. It's in this direction, that is the direction of a velocity. Now, all you have to do, just do this now. Let's space it out a little. So good man, B, V, magnetic force. Basha, is the direction good man it is positive X. According to the diagram, of course, direction magnetic force it is negative Y, right? Because low khali baba, it is downward here, so downward is mabasni. Down the page, Basha, which is negative Y. Kata magnetic field we have X and Y. Kata magnetic field must be Z. Is it Z positive or negative? Now you can find it out, of course, using the right-hand rule. So always start with the magnetic force magnetic field directionally magnetic force baba, it is obviously pointing y negative, that is the direction is positive, so baba in your palm directionally y negative basha the directionally motion and velocity baba, it is x positive, right? So this is z, it is incorrect, so I'll just have to do this one. Now the thumb is pointing toward x positive, magnetic field is that the beta out of the pitch. Magnetic force it is y negative, velocity is x positive. Cut in this case, of course, the four fingers would point upward, which means z positive or out of. We can say out of the pitch. Basha, because so see whatever that is given. If upward is given, you could use upward. If out of the pitch is given, out of the pitch. If not, z positive, and that'll be the answer to this question. That is this simple, obviously, Bashwala. So that's it, Yani. Now, going to perhaps maybe some other questions. These questions, all of them are related to the questions we were been solving. Let's start from the bottom to the top here. It says, what is the path of an electron moving perpendicular to a uniform magnetic field? Man, whenever a charge moves into a magnetic field at a right angle, the straight path, circular, ellipse, and parabola. Man, obviously it is going to be within a circle, because it says perpendicular. We've learned that whether proton or electron, magnetic field at a right angle, it will end up moving in a circle. Or the fifth quote, the question 5 says, the magnitude of the electric force on a charged particle that is moving inside a uniform magnetic field is 0. When will it be 0? If the angle between the direction of the particle's velocity and the direction of a magnetic field, direction and the angle between these two must be what for the magnetic force to be 0? And of course, if they're parallel, and if they're parallel, then the angle will be 0. The proton moves at a speed of this much at a straight right angle inside a magnetic with a magnitude of 1. Define the acceleration of the proton. Find the acceleration acceleration we can say magnetic force Fe translation Q V mass times acceleration. They define the acceleration of a proton. They should have said find the magnitude, by the way, because acceleration has both magnitude and direction. Find the magnitude here. And what is the magnitude? Acceleration Q VB over the mass. Do we have the charge? It says a proton, yes. That is 1.6 times 10 to the power negative 19. What about the speed here? That is 2 times 10 to the power 7 here. You could do that at right angle, so sine to a magnetic field with a magnitude on the magnetic field. What about the mass of a proton? Mass it is 1.67 times 10 to the power negative 27. Charge so do the math, of course, you'll find the answer, and that is this easy. All right. You give them a try, of course, you can do them very easily. What about this one here? I think we've tried this one. Question 3 says, at which angle between the direction of a uniform magnetic field and a positively charged particle charged particle's movement, the magnetic force on a charged particle is half of maximum. Let's get the half of maximum, Baba. Half of maximum. I get angle like 90 b, that'll be max. I get it. If it is 0, that is going to be 0, right? So minimum. What if it is 30 degree? If the angle is 30 degree, is going to be what? Is going to be half of max. I got to leave that. Half of max, which I believe you already know this one. Got B would be the correct answer here. What about question 2? Let's take a look at this question 2 and see what it says. An electron, it says an electron in an electron beam experiences a force of this much while traveling perpendicularly uniform magnetic field of this much. What is the approximate speed of the electron? Charge of an electron is this much here. Electronic money, Baba. Remember, force here. Perpendicularly, angle like 90, you don't have to write it down. Magnetic field man here. What is the approximate speed here? That's the equation here. F magnetic Q VB sine speed that is magnetic force over what? Over Q times B. Over this, of course. Magnetic force here. I'm gonna write it down. That is what it is. And then charge here. It is an electron, right? So here's 1.6 is given here. Magnetic field of Kesher is this much. So you just write the numbers, plug in, and then do the math. You'll find the speed, which is going to be meter per second, and that's it. And pretty simple, actually, these questions. All right, I guess that'll be the end for this session, right? Inshallah, next time we're going to continue from this point on. Till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.